All right, guys, gonna do an ANOVA demo here. So on my stat lab, you, now you'll probably, let me back up a little bit here. You'll probably want to access it through homework, but this is not available yet. And again, I'm teaching this for my fall class, so if you're taking this in the summer or the spring in a future semester, whenever this ANOVA assignment comes due, this demo will become available. But it's not for credit. It's just it's kind of for you to learn. So let's go into preview, and I'll work some of these problems, and hopefully you'll learn something from it. So an experiment has a single factor with 5 groups and 8 values in each group. How many degrees of freedom are there in determining the among group variance or variation? So if there's 5 groups, that means C minus 1 will be the. All right, this is not going to work. I'm going to have to keep. Okay, that's going to bug me. There is R blank degrees of freedom in determining the within groups. So we've referred to this as the denominator. So this is the total sample, total sample, which is 8 values in 5 groups, so that's 40, minus the number of groups, which is 5, so this is going to be 35. And of course, next it's probably going to ask the degrees of freedom for the total variation. You guys remember that's just these two numbers summed, or it's the total sample size, 8 times 5 is 40, minus 1. In either case, we should know now that that's 39. All right, hospital is a main campus in 3 satellite locations. Management wants to reduce waiting time for ER cases. A random sample of 11 ER cases at each location was selected and the waiting time was measured. All right, so it says click the table. Well, see, we don't need any of this critical value stuff because we use StatCrunch, but I do want to get my data. So I'm going to open it up in StatCrunch. Guys, as you know by now, I don't like the data this way, so I'm going to arrange it, and I'm going to stack it. Now, I want my values, I'll call those wait time, because that's what they are, and store labels as hospital. So I have all the measurements in one column and my hospital in another. So guys, I'm going to go edit, column, delete. And you don't have to do this. I do because I'm just kind of a nerd. I just don't like those there because it just tackies things up for me. But I'm just like that. So that's the way it is. Alrighty, so first of all, check what are the hypotheses. Well, we know that the null hypothesis has to be all equal to, and let's see, not all mu sub j are equal to where I equal 1, 2, 3, and 4. So since there are 4 hospitals, we would choose the subscripts 1, 2, 3, and 4. All right. Find the test statistics. So guys, I'm going to run an ANOVA. I'm going to go ahead and get all this stuff. I don't need it just for the test statistic, but I may need it later. So the test statistic is 6.5534. So 6.55 through, okay, it only needs 2 places. Calculate the p-value. Well, that works out nicely. 0.0 0.001. So we do have significance. So since the p-value is less than alpha, we reject the HO. Sorry. So there is sufficient evidence to conclude there's a difference in wait time for hospitals. All right, if appropriate, determine which locations differ at a 0.05 level. Well, when we go to our post-hoc, we can see that the main and satellite 1 are significant. The main and satellite 3 are significant. And that's it. So the main and 1 and the main and 3. So the main and 1 and the main and 3. All right, that should be it. At the 0.05 level, is there evidence of a difference in variation? Well, let's go back to Levine's. Levine is greater than 0.05, so there's no evidence of a difference in variation. So we will choose pretty much a similar null and alternative hypothesis. The F statistic is 0.44, 0.03. Let's see how far it wants us to go. .44. The p-value is going to give us problems. Well, guys, it just dawned on me that what the author does is uses a modified Levine's test, where I use the standard Levine test. Now, the difference is when you study statistics at maybe a little bit higher level, you get into parametric and non-parametric types of analyses. And it's my opinion, the way that I was taught, that when you can assume normality, that you use Levine's test. Now, if you get into situations where you can't assume normality, then you get into a modified Levine's test, and you get into non-parametric kind of stuff. So it's dawned on me that we are going to report 0.725. I don't know how many places it wants us to go. 3 places. So we're going to report 0.725. And it's probably going to count it wrong. 734. All right, guys, I don't want to deal with this. This is I don't like that. To me, it's a fundamental issue that's wrong with this textbook. So here's the deal. When you do this, and if you don't get it wrong, now you can investigate calculating the p-value for the modified Levine's test. What they do is they take the absolute value and just sum up some stuff, and it's just really irrelevant. I'm not even going to go through it because I don't want to cloud your brain. But what I will do is if you miss this problem, and I think there's going to be actually a couple of problems where you report the p-value for the test of equal variation, then just email me, and I will go through and correct it. So, hey, I'll get to see who's really watching the videos too, because this will be kind of one of those embedded, informal, sneaky quizzes. So if I get an email from you, I'll go through and give you full credit. So, guys, since the p-value regardless is greater either way, whether it's the modified or the straight Levine's test, is we do not reject, and there is insufficient evidence to be concerned with the variation. All right, question number 3. Well, that's it. No, it's not it. Okay. Sporting good manufacturing company wanted to compare the distance traveled by golf balls produced using 4 different designs. 10 balls were manufactured for each in order to pro denote which they were hitting the results. Okay. So guys, we have 4, so we have mu1 equal mu2. Not all mu_j are equal, so that clearly seems to be the right choice. F statistics. So guys, let's get some data. And I'll tell you what, I'm gonna demonstrate how you can run an ANOVA this way, just to kind of mess it up a little bit. So I can go ANOVA one way, but this way I can do select all columns. I still want to compute Tukey, and I still want to do the equal test of HOV. Maybe they've got, nah. Okay, let's compute. And the ANOVA we get is very, very, very small, the p-value. So we have statistical significance. Golly. The F statistic is 53.389. So 2 places, so 53.39, I guess. All right, p-value. P-value is very, very, very small. So to 3 places would be 0.000. So the p-value is less than alpha, so we reject the null and conclude there is a difference. There is sufficient evidence to conclude a difference in the means. All right, the results at the 0.05, where do we find the differences? So it looks like we have the differences in everything except 3 and 4. So all the differences are significant except between 3 and 4. So 1 and 4, 2 and 4, 1 and 3. So all of those appear to be significant. What assumptions are necessary? Well, guys, we need normality. We need homogeneity of variance. We like equal sample sizes. That's called a balanced design. We don't have to have that, but we definitely have to have randomness and independence. Here we go. We're going to have more fun with this modified Levine's test. It drives me insane. So guys, we have 4 groups, so we look for subscripts of 4. Find the test statistic. The test statistic will be the same, 2.329. 3.2, no, hold on. 2.33. All right, let's see again. There it gets into perform a one-way ANOVA on these absolute differences. Guys, we're just not going to do that. I don't. If we had a non-parametric design, yes, but no, we're not doing that. Let me check one thing to see. I'm going to do a little toying around here. So let's go to edit. Thanks, Megan. And let's try the Brown Forsyth. I know this isn't going to work, but I just want to try it anyway. So 2.06. Okay. The p-value, 0.123. All right, guys, there you go. That's frustrating, but all right. Let me tell you what's going on here. Uh, Again, it just goes back to what kind of design you're running. And I know it's complicated when you're trying to learn this stuff, but uh, for some reason, this author is, yeah, I've never seen this happen. I find it very interesting. I've never seen this happen. That when you assume normality, and everything that you're working with assumes normality, that you run a non-parametric test randomly. So, guys, so there's definitely a kind of a sneaky quiz included, because you're not going to get these right. If you run a Levine's, you're going to have to run the Brown Forsyths. So that's frustrating. But what I want you to leave from here is, if you go out and do something and you're running into an ANOVA and you run a post-hoc run the Tukey HSD, if you do a test of equal variances, I want you to run Levine. So anyway, our p-value is greater than our alpha, so we do not reject, and there is insufficient evidence to conclude. So I'm at a kind of a crossroads here about whether to go back and redo all the videos just so I can appease the author. I'm not going to do it because I don't think it's right. I just don't think it's right. And at the end of the day, you're taking the class from me. So I'll tell you what. I think I am going to inject a sneaky quiz here, because I want to know that you understand what's going on here. So I want you to type the following information to me. This is sneaky quiz number 5 or 6 or 12 or 50 or whatever it may be. So sneaky quiz, I think it's number 4 or 5. Let me go back to Assignment Manager and see. So the last sneaky quiz was quiz number 4 is the notebooks. This will be quiz number 5. So quiz number 5, I want you to write something to the effect: I understand that Levine's test for equal variances is appropriate and most commonly reported for ANOVA. However, if we cannot assume normality, then the Brown-Forsyth or the modified Levine's test may be appropriate. This is ridiculous the way that the author's presenting this. I know no other way to say that. Levine's is the staple, and you use the modified if there's reason for you to use it. You don't use the modified, then go out and search for reasons for Levine. So, because of the assumptions. Assumptions are you have normality. So, all right, enough of that. I'm not real happy with this textbook right now, but I'll get over it. So what golf ball design should the manufacturer manager choose? I go back to the so 1 and 4, 2 and 4, 1 and 3. I'm going to go back to the sample means, and looks like to me that either design 3 or 4, would be my choice. They have the higher sample means, so we do have significance. So, I would choose. There you go, first one. I choose design 3 or 4. Because the mean distances are both significantly greater than those of 1 and 2, but are not significantly different from each other. So, yep, I think that is the appropriate conclusion. All right, guys. I know that students hate these types of questions or these types of issues, but I promise you, I think I'm steering you correctly. Either that, or I need to take my PhD back to the University of Kentucky. I don't know. But anyway, it is what it is. So, guys, get that sneaky quiz to me. Just tell me, you can rewind to me and type in what I just stated. So, all right, I'm done. I'm going to get off here and just go be pissed off, right? Take care.